Good morning. So, nice to be with you guys again. The persistent, the sticking with it. I appreciate it. It keeps me going. Um, let's see. Before we jump into what we're going to talk about today, does anybody have any questions or any concerns or anything? Let's see. Uh, your last quiz is live right now. Um, and you'll have a couple days. It's on energy conservation and work. Your last homework assignment is posted. It's basically half of an assignment because I don't want you to be worrying about uh, like full homework and getting everything, if you have outstanding stuff done and, sort of wrapping everything up at the same time. So the last homework assignment is sort of a little bit abbreviated, but that's okay. It's enough to give you a flavor for the topics. Um, yeah, a number of students have reached out with regards to missing labs and stuff and have made appointments. So if you're missing anything, this would be a great week to set up a time where we can chat about it and get you um, get it straightened out. Um, like is mentioned in the chat, we're getting there. We're only uh, this is our last week of regular quote unquote regular class. Um, yeah, this is the last week for lab as well. So everything's kind of winding down. So I think if we can stay 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 the course, stay strong, we'll be in pretty good shape. I'm pretty supremely impressed with folks who are getting up and watching streams at 8 o'clock in the morning from the comfort of your home where you don't necessarily have to do that. So kudos to you guys. You're doing that definitely keeps me motivated, so I really appreciate it. So the final's next week. The exact schedule for the final isn't pinned down. I'm still deciding how long to make it available for. But after what I've seen in the survey and talking to folks and stuff, and just talking to faculty too, I had mentioned that I'm a little concerned that it's going to be that a lot of students are going to have like finals back to back synchronous finals where they have to like upload stuff. So we're not going to do that. We'll do something more like the quiz where you have it available for a period of time and you need to complete it in that period of time, but it won't be synchronous. I just think it's gonna. Yeah. I think the possibility of there being logistical issues between classes is too big to risk that. So, and it'll probably be due on Friday. I would imagine. I don't see why any reason to make it due earlier. That way, students would have as much time really as we can because the quarter ends at the end of the week, so the end of that week. But yeah, that's a good question. Stay tuned for more exact details on that. Let's see. Other questions? Logistical questions, questions about outstanding stuff. One thing I want to mention, or it just occurred to me, some students have contacted about missing homework. If you have homework assignments that you haven't finished, you can get work on those too. You'll still get most of the credit for it. So the idea with the homework, the due dates with homework is that it's about 90% just to try and incentivize not getting behind. It's less about like oh, the physics primer, it's not required, no. That's an assignment that was an assignment that we've had available the whole quarter that was like introductory topics, but it's not worth any points. So it's not required. But what I was going to say about homework is, the rationale with that was just to mostly encourage students to get it completed, and so that you don't get behind, because the course can be kind of grueling once stuff starts to accumulate. So, but if you have some outstanding assignments that you're like, why bother finishing them? It was due a week ago or something. You can still get most of the credit. So, as we, kind of wrap up for the quarter, part of the thinking with having a short last assignment is that that would give you a little room to finish up other outstanding homework. Yeah. So the physics primer is not required. It's just practice. Other questions? You guys ready to rock here? Yes. You didn't have to do the corrections for credit. There have been some consistent problems with the gradebook in terms of incorporating that. I'm going to be checking the gradebook for glitches and errors. So uh, that may be a problem. Let me make a note of that again. Yeah, sorry about that. That's been a recurring annoying situation. For whatever reason, when it calculates the average, if there's no grade, it doesn't incorporate it, which makes sense. So like if you get an A or whatever on the quiz, you wouldn't average it with corrections because you wouldn't do corrections. But the gradebook keeps defaulting that when there's nothing, it makes it into a 0. We're not going to redo other quizzes, but let me study the gradebook and see if there are some grades for grades that are really low, where it's really dragging you down. We might be able to come to some arrangement, but I don't want to have corrections for everything. These are excellent questions. This reminds me of some things I want to make sure that are squared away before the end of the quarter. Other questions in that vein, logistical things? Another thing would be that you could do is just check the gradebook and make sure there isn't anything missing that you're like, I turned this in. Because students have noticed some things like that. Either glitches in the gradebook or errors on my part or, Blackboard issues or whatever. So I'll try and just make sure that everything is as we expect because I don't want anybody to be, docked for some technical problem. That would be dumb. All right. Let's uh let's roll here. So we're going to talk about rotational motion. Um, the last week of class, basically what we're going to do is we're going to touch on a number of things, but it's kind of cool because in a lot of ways it's stuff that you already know, uh, except now it's in the context of rotating objects. So a lot of the same ideas. So we can look at kinematics, i.e. mathematical description of motion. We can talk about energy. We can talk about momentum. We can talk about all of these concepts in a rotating system. And so the first thing that we're going to talk about is kinematics. So, and this is in chapter 10, and this is the first few sections of chapter 10. And we had touched in this, so for context, we've talked a little bit about this. If you recall, in the latter half of chapter 5, in particular, centripetal acceleration. Recall centripetal acceleration, the magnitude of that was given by the square of, velocity over r. And we use this when talking about gravity principally, but also rotating situations where we wanted to calculate the force required to allow something to turn, i.e. things like an object on a string that you're spinning around, etc. And if you recall, one of the difficulties when we worked with this with regards to gravity is that oftentimes it's kind of weird to talk about velocity. Like if you're talking about a satellite, for example, you often don't know the velocity of the satellite, but it's logical a lot of times to talk about the period. So basically what this rotational kinematics does, the main conceptual addition or jump here is to think about angular quantities instead of things like velocity. So let me say, let's put it this way. Not contribution, addition here is think about angular quantities. And this has an advantage because when we're talking about centripetal acceleration, for example, v depends on r, right? So, for example, if you're here, if your r is to here, let me try and draw a better picture here. Like this r versus this r, the velocity at 1 is not the same as the velocity at 2 because it depends on how far out you are, which makes analyzing a lot of rotational problems a little more complicated because if you're talking about some object that's rotating, if you think of it in terms of the velocity of a point on that object, the velocity of every point as you go farther and farther out is going to be greater. It's just cumbersome to work that way. So instead, what we do is we talk about rotational quantities. So, and the first rotational quantity is, if I can draw a circle, is theta. So before we had talked about this, that if you go all the way around 2 pi r equals the circumference. Well, we don't have to go all the way around. We can talk about this in terms of a portion of a rotation. So let's imagine now we just go from here to here. It's still r. Now this is some angle, theta. So theta r is going to equal, we'll call it L, an arc length. And this allows us to define the arc length, this allows us to define theta as L over r. Now, theta, it doesn't matter. This is an angular quantity. If you imagine this thing is like, imagine this thing is like a plate or a disc or, a turntable or something. It doesn't matter where you are on that. If you rotate it some amount, each point on there is going to rotate through the same angle. And it turns out that we can talk about basically all of the quantities that we looked at with regards to kinematics in Chapter 2. We can talk about them in terms of this rotating system as well. So there's there's rotational analogs to all of our things that we talked about. So, for example, let me give you kind of the definitions. So the first one, well, here, let me provide it to you as, recall when we talked about this in chapter 2, we talked about displacement, x. Well, and I'd mentioned we talked a little bit about this in lab last week, so this is going to kind of flesh that out. That was pretty quick. We talked about it in regards to the pendulum, but now we're going to add a lot more detail. So displacement becomes theta, angular displacement, velocity. Oh, let me give you definitions here too. So comes angular displacement. Velocity. Now velocity is angular velocity. We use the letter omega. And angular velocity, the definition for that is, if we're talking about the average case anyway, that would be the change in angle per change in time. And it's given by the Greek letter omega. In X, Y, and Z in chapter 2, we talked about acceleration. Now we have alpha, which is the variable I mentioned in lab last week, where alpha is the angular acceleration. And if we're talking about the average case, this would be, the change in omega per change in time. And, you could imagine these all have instantaneous counterparts as well. When we talked about velocity, there was both the change, an average velocity, a change in displacement per time, but also you could take a derivative of the displacement and that would give you the velocity. You can do the same thing with this. You can look at the instantaneous version of these as well, where omega would be more precisely defined as d theta dt, alpha would be d omega dt, etc. So this may seem kind of complicated, but really what I want you to feel like is new, but you really know a lot of this math already. So, let's see. So I want to make a couple connections to things that we've already talked about. So one thing is we want to connect the tangential acceleration. So we talked about this in lab. So the tangential acceleration is R alpha. And this is the connection that we used in lab to connect between, I've been saying connection a lot. This is the relationship that we used in lab to connect between the acceleration of the pendulum and the acceleration in angle, alpha. So let me draw a picture to help you kind of see this. Let me use a different, well, let's see. So basically, imagine now you have, instead of a pendulum, it could be a disc, or it could be a pendulum. But what we're interested in is so I'm gonna do my best here to draw a picture that includes both the tangential and centripetal acceleration. So the tangential acceleration is R alpha. And this would be the component of the acceleration that is in the same direction as the velocity. So remember when we talked about this in regards to centripetal acceleration, we almost always assumed that the velocity was not changing, i.e. you're spinning around in a circle at constant speed. In that case, you wouldn't have a tangential acceleration. Let me put in our other quantities here too. So we have velocity. So recall the velocity is going to be r omega. So the velocity of a point here. And then the other one that we had is the centripetal acceleration, where we used AR to designate it for radial. But let me just write it out as centripetal. And this is the one that's directed towards the center. And it's given by v squared over r when we talked about it before. Well, we can substitute in here r omega squared over r. And then this becomes, we'll cancel that factor of r omega squared. So this gives us a new way of writing the centripetal acceleration. And in a lot of ways, it's more convenient because, like I was talking about above, omega, these angular quantities, it doesn't matter where you are in the object, how far you are from the center, as opposed to when we're talking about it in terms of velocity, every point on that spinning object is going to have a different velocity. So this is just maybe a better way of communicating this idea, although it requires us to introduce, some new concepts. So that's one connection. And then another connection is recall from when we were talking about gravity, we made use of this all the time. The fact that the period for an orbit or something like that was 2 pi r over the velocity. Well, we can put in the fact that the velocity is r omega. And then we would cancel a factor of that. And now we have 2 pi over omega equals the period. And this is something that we talked about in lab as well, but it's good to just refresh these definitions. And then if we, we can do things like recall the frequency will be 1 over the period, so that'll be omega over 2 pi. So we talked, you may have encountered this before in math, I suspect, but this just gives us a connection between frequency and angular frequency. And a lot of this is just more natural in terms of the angular quantities than it is in terms of things like velocity. So this, this is a pretty fundamental piece of math, or equivalently the fact that omega is 2 pi f. So this appears all over the place. We encountered this when we were talking about an oscillating object. Yeah, so that's a couple of connections between things that we've already messed with and this angular velocity, angular centripetal acceleration, etc. So we've added this ingredient of the tangential acceleration. We pretty much assumed that that was 0, that things were spinning at a constant velocity before, and now we've added that in. So let me show you an example where we make use of these definitions. I feel like it's kind of a lot of vocabulary, so I want to show you what this looks like. So a useful example, I think, to think about these different terms is a record. Some of you probably, or it's funny, records are becoming more popular again, but y'all know what a record is, yeah? So they're called LPs a lot of times, and that stands for long play. And LP records spin at 33 1/3 RPM and are 12 inches in diameter. And we can look at basically these different definitions for records. So we can find the frequency in hertz of revolution. We can find the angular frequency. We can find the speed at a position on the edge of the record. We can find the acceleration, i.e. A acceleration tangential. We can find, and then we can think about this question of, are the grooves constantly spaced? So let's look at these different components. So the frequency of revolution, we're looking for f. So this gives us an opportunity to connect. One of the units that you encounter a lot in rotational motion is RPMs. And this is, you'll end up converting between RPMs and revolutions per second, i.e. hertz, a lot. So this gives us an opportunity to exercise that. So we have something that's 33 1/3 revolutions per minute, i.e. RPM. Well, in 1 minute, there's 60 seconds. So that's 0.5. Draw here. 0.56 revolutions per second, i.e. times per second, so 0.56 hertz. A lot of times in a frequency, you're talking about like cycles or revolutions or something like that, and it's sort of assumed, or they're not necessarily really explicit about what it is. It's just that you have that number of cycles per second. The angular frequency in omega. So omega. So to find omega, remember omega is 2 pi f. So 2 pi times 0.56. 2 pi is about 6, so this should be about around 3. A little more. When we crunch the numbers, we find that it's 3.5 radians per second. So again, I was a lot of times with regards to angular velocities, they're not very explicit about the units. But if we're talking about an angle in radians, then technically this unit would be radians per second. And I would say, you basically never do angles per sec, like degrees per second. The unit that you want for this is radians. So we also want the velocity. So velocity for a point on the edge. So let me just draw a picture here. If we're talking about excuse me, sorry. This velocity is r omega. So now if we have omega, the velocity is going to be half of our 12 inches. So we're going to want to convert that into a normal unit. So we have 6 inches. You can use whatever your favorite conversion factor is. I tend to remember that there's 2.54 centimeters in an inch, which is another way of saying 0.0254 meters per inch. So multiply that times our omega. So this is going to give us a unit of meters per second. When we multiply that out, we find 0.53 meters per second. Yeah, just to fill out our picture, this is omega. Part 4 is asking for the acceleration on the edge. So in other words, that's the tangential acceleration. Oh, wait a second. Actually, we'll just do them both. So if the thing is spinning with constant omega, there isn't going to be an angular acceleration, but there will be a centripetal acceleration. So in other words, alpha equals 0 because it's constant omega. So r alpha equaling at is also going to be 0. Or let me put it this way. The tangential acceleration is r alpha, and that's going to be 0 because alpha is 0. However, we're still going to have a centripetal acceleration. Let me put that one in a different color. That's what we've been doing in the past. So the centripetal acceleration, AR, for radial, that's given by r omega squared. So remember, we've been accustomed to calling this v squared over r, but we can also now write it as r omega squared. So that's going to be our 6 times 0.0254 divided by 1 times our omega. So our omega was 3.5 quantity squared. This will be 1.85 meters per second squared. So questions. So we know omega is constant because the thing is spinning at a constant rate. If it wasn't, then your music would slow down and speed up, and you would hear that. But this gets at the last part of the question too. So, or if you ever played with a record player, and like if the needle's sitting on the record and you turn it on, you'll hear it spin up, right? You'll hear it accelerate. That would be a tangential acceleration. You know, as in terms of the radius isn't not changing. The thing to think about that is, or that lets us talk about this last bit of the question. Are the recording grooves for a song encoded on the edge different from those for a song recorded towards the center? If so, how? So if you think about it, the velocity, i.e. part 3 here, is calculated r omega. So if omega is constant, i.e. the record isn't speeding up or slowing down, it's the same, it's spinning at the same rate, but r is going to change as you go towards the center. So in other words, so we could think of it as like, here's one velocity and here's another velocity. So for a point on the edge, you know, it would be the same as what we calculated. But suppose V2 was halfway in, then we would have 1/2 times 0.53, and it would not equal V1. So in order to deal with that, the fact that the velocity of the needle across the surface of the record is changing as you go towards the center, because that's how you read it, right? You read, you know, from the outside towards the center. As a result, the grooves are not constant. So they have to be spaced out more as you get towards the center. So so it may be helpful to think of that you know, like digitally, like if we imagine a pulse train, if you were scanning over that at a different speed, you would want to spread the pulses out. You know, if you're going slower, they would have to be spread out more. Or they would have to get closer together. I might have that backward, but you get my drift. Since the velocity is changing as you change your position on the surface, you have to change the encoding in order to deal with that, which is kind of interesting. And it'd be the same thing with CDs. You know, if the CD is spinning at a constant rate and you change where you're reading it out, that's going to change the required spacing of the pits and the reflective spots on your CD. So hopefully this kind of gives you a sense for these different terms. We've kind of, some of this is a little bit familiar because we dealt with it in chapter 5, but some of it is not. So questions so far? So if you have a record player at home, you can dust it off and think about these same ideas. So that is in revolutions per second or hertz. A lot of times when you're talking, like I said, it's sort of hertz is usually discussed as cycles per second. So you can think of this as revolutions per second or cycles per second. But anything, number of times of something per second is hertz. Yeah, this is the unit that I would stick to. 1/seconds, hertz. So the reason that it's kind of vague, or part of it, is to think about like our pendulum, right? So with that, it wasn't. It was a cycle, a back and forth per second. It wasn't going in a circle per se. So that's why I've mentioned them both. Yeah. So these are all kinematics for quantities for things that are rotating. Yep. About an axis. Yeah, exactly. So the thing I want to add to this next is it's kind of interesting because it's stuff that you already know. So part of why I like talking about this at the end of the quarter is because it actually gives us an opportunity to review some stuff that you already know, and it's way back from chapter 2. And what we can do is uh, constant alpha, angular acceleration. The math to describe that is just like constant acceleration. So recall from chapter 2, we had built up some expressions. Like velocity is initial velocity plus acceleration times time. Well, the angular counterpart to that is omega equals omega naught plus alpha t. Okay. We had x is v naught t plus 1/2 at squared. Plus an x naught. Well, theta is omega naught t plus 1/2 alpha t squared. And you can think of this as having a theta naught, although a lot of times it's, since angles fold back on themselves, right? They repeat. It's less, it's not. It's a little bit different than like a distance, where you've already moved some distance. We had from chapter 2 this one, v final squared is v naught squared plus 2 acceleration times distance. Well, the angular equivalent of that would be omega squared is omega initial squared plus 2 alpha omega. And then the last one in that chart in chapter 2 was for constant acceleration, we could find the average velocity from the initial and final velocity. You add them up, divide by 2. Well, it's the same situation for angular quantities. Add the omegas, divide by 2. So this is, you already know these expressions. You know how to use them. All you have to do is figure out how to translate problems, angular problems, into this math, and you can solve problems with it. So let me show you an example or two. So a couple examples. All right, sorry. So we'll show you a couple examples here. So here's one. Try and leave. So we won't have to use our kinematics quite yet, but a 64 centimeter diameter wheel accelerates uniformly about its center from 130 to 280 RPM in 4 seconds. Determine its angular acceleration and the radial and tangential components of the linear acceleration of a point on the edge of the wheel 2 seconds after it has started accelerating. So part A, we want to find the angular acceleration. So this is the change in angular speed divided by a change in time, if we're talking about an average. So for this question, that would be our final omega minus initial omega over a change in time. Now this is where, recall, we'll have to convert between RPM and revolutions per second. So 280 RPM. So there are 2 pi per revolution times 1 over 60 seconds per minute. So let me actually write this as revolutions per minute, just so it's clear. You know, you cancel the minutes and the revolutions, and we're left with a unit of angle per second, which is what we want when we're talking about omega. So that's the change in omega, and then the change in time was 4 seconds. So this would leave us with an alpha of 3.9 radians per second squared. And then we need to know, oh, I should draw a picture here as well. Let's see, we have, oh, we're almost out of time. I should have drawn a picture to begin with. It's always a good idea to have your, to have a picture. So we've been calculating, the angular acceleration alpha. And then we also want to find the radial and tangential components. So in other words, we want a t and a r. So AT is R alpha. So if it's 64 centimeters in diameter, that's a radius of 0.32 meters times our 3.9 that we just calculated would give us 1.25 meters per second squared. And then our AR is R omega squared. And this would be, so we need to find the omega at that particular time. So that'll be R times, so omega is going to be omega naught plus alpha t. That whole thing will be squared. So this is R. So omega naught was 130 times our 2 pi over 60 plus our alpha is 3.9 times our t, which is going to be 2, because we're talking about 2 seconds after it started accelerating. So if we put those numbers in and crunch the numbers, we would find that the centripetal acceleration, i.e. the radial acceleration, is 147 meters per second squared. So that's the one that's directed in. And this is the one that's, tangential. So let me just put this in a different color just to emphasize this. Okay. So, yeah, I don't want to go over too long, but I think you see how this is directly analogous to what you did in Chapter 2. We can look at the angular counterparts to all of our quantities, kinematics quantities. Velocity becomes omega. Acceleration becomes alpha, angular acceleration. And we can solve problems like this, where you have an object that's spinning. You can figure out how far it's gone, i.e. theta. You can figure out its acceleration. You can ask a lot of the same same flavor of questions that we looked at in Chapter 2, but now in the context of rotating things. So I don't want to go over too much. I'm trying to be better about the time, but how does that seem? Does it seem familiar in a way, or does it seem totally new, or what do you think? Is the sound not working? Oh, that's kind of weird, because we talked about radial. Ah, no worries. Yeah, so it's weird. It's a little bit different, but yeah, I think the tangential is a lot more intuitive. It makes sense. If you speed something up, you're going to have a component, an acceleration that's in that direction. I think the radial, the centripetal acceleration is a lot more difficult to conceptualize. Yes, exactly. I think that that's a good point. The challenge for a lot of, it's almost more difficult when you have things that are similar than when they're not, because it's easy to get them confused. So that's definitely a thing that we'll practice. And I'll try and distinguish between those when we're talking about them by doing things like using different colors or tricks to try and help you see, which is which. But yeah, that's an excellent observation. I agree. Keywords That's a great question. So acceleration uniformly accelerated, that is another way of saying constant A or constant alpha. So that allows us to use these expressions. Recall, if acceleration isn't constant, then we can't use that algebra. I mean, that's about, of course, tangential, radial. Edge is telling us that we're looking at the radius. I would say that the language is a little less tricky than it was with regards to stuff like energy conservation. Some of those questions had, there were kind of keys to jump on. But we'll look at some more example problems next time. And like I said, the homework assignment for this week is really concise because I don't want you to be worrying too much about a bunch of new stuff. We're kind of winding down. But it is really interesting stuff because it's almost review at the same time because you know a lot of kinematics, you know about forces. We're going to talk about the angular equivalent of force next time, torque. So start reading chapter 10. And we'll talk about some more examples next time, get into torque. We don't have the time to go in as much depth as we did with forces, but that's okay. This is sort of a concept that's built on top of that. So, other questions? I should wrap this up. I don't want to step too much on the passing time. So, of course, if you have questions, you can contact me on Teams or email. If you have questions about outstanding labs or anything like that, let me know and we'll get them worked out, this week and next week. So, otherwise, have an excellent day, and we will see you Wednesday or in lab tomorrow if you have lab tomorrow. So, yeah, have a good day.